Thank you for the introduction. I'm Riccardo. I'm originally from Italy, but today I'm visiting from the University of Colorado Boulder, where I'm a third-year PhD student under the supervision of Dr. Hans-Peter Schaub, whom I would like to acknowledge as my co-author, and Dr. Cody Allard from LASP. I was also in the competition for a presentation with one of the longest names, to the point where they asked me to change it. So yeah. It's not matching what's on the website, but that's still me. So I would like to start by describing the framework in which this work is implemented. That is Basilisk Astrodynamics Simulation Framework. So what is Basilisk? Basilisk is some open source software that is currently being developed by the ADS lab at CU, which I'm part of, and also LASP, from whom we also had a very nice presentation yesterday. Why the name Basilisk? The name Basilisk is to hint at the dual nature of the software, which has a higher level Python interface, which is combined with a C and C++ core to execute all the functions. Sorry about the C and C++. If you suggest that we should change it to a different programming language, I can be convinced, but you would have to talk to my advisor, and good luck with that. Having said that, what's the main strength of Basilisk? I think one of its main strength is its modular structure. And in practical terms, what it means is that every segment of code is encapsulated in what we call a module within Basilisk. Effectively, a module is either a C structure or a C++ class, where all the math happens inside this enclosed container. And this limits the coupling between different code segments. So all the information that flows between different modules happens through what we call messaging system. Each module has input and output messages. Messages are effectively C structures, so the information that they contain is very strict. Each module reads in input messages and writes out output messages, and that is the information that can be exchanged between different modules. Typically, flight software modules are written in C, whereas C++ is used to simulate dynamic components. Basilisk also comes with a nice simulation rendering tool, which is called Wizard, which you're going to see towards the end of this presentation. What is Basilisk used for so far? It's used to model complex spacecraft dynamics. It's used to support mission concept development. It supports hardware-in-the-loop testing via very high-fidelity simulation of these hardware components. Analysis of flight data versus expected behavior, and also to support, more recently, to support AI-based autonomy development. I should say that currently the inspiration for Basilisk is to provide a high-fidelity simulation framework, but some of the flight software that to this day exists in Basilisk has been flown in LEO and in deep space missions. So the effort was to take the heritage that came from, I should say, the early stage developments of Basilisk and develop it into something that is open source and can be used by everybody. Couple words about me. I am part of a team of students that has been given the opportunity of working on this very exciting, in my opinion, mission, concept, design, and development. As it will be clear from this presentation, I come mainly from the world of spacecraft attitude dynamics and GNC, so not so much from the flight software world. Please keep that in mind as you grill me with questions at the end of this presentation. Having said that, I was involved with designing most of the flight software modules that revolve around the attitude control for this mission. So without further ado, what is this mission about? This mission has very complex pointing requirements that arise from the very complex geometry of the spacecraft. This spacecraft features a hub, 4 reaction wheels in a pyramid configuration, which are what allows to to control the spacecraft attitude, It features two rotating solar arrays. These solar arrays are mounted on an axis that is fixed with respect to the spacecraft hub, but they can rotate about this axis in order to maximize the incidence of sunlight on the power generating surface of the solar arrays. There is a dual hinged platform, which is there represented by that purple box. This means that this platform can rotate with respect to the spacecraft hub, so it has 2 degrees of freedom with respect to the hub, and there is a solar electric propulsion thruster mounted on such platform. Obviously, the primary purpose of the solar electric propulsion thruster is to keep us on the interplanetary trajectory that we want to achieve, but also the fact that this thruster can be gimbaled and its direction can be oriented with respect to the hub allows us to perform more interesting tasks such as momentum dumping. So we can double use the thruster for multiple purposes. As I was saying, the spacecraft is on an interplanetary trajectory, at least in this part of the design, and solar radiation pressure is acting on the system. This is important because we have very large solar arrays, so that cannot be neglected. This is a block diagram that describes most of what goes into the attitude GNC aspect of things, but it doesn't even get close to describing everything that that will eventually go into the spacecraft. But to summarize what we're looking at here, in yellow, we can see our favorite stuff. Those are flight software modules that basically compute references for each of these moving components of the spacecraft. Whereas in blue, we can see simulated dynamic components, specifically the platform and thruster assembly, the reaction wheels, which then control the spacecraft, and the solar arrays. Everything else is, well, there's not much more than that, but there are simulated external forces and torques acting on the system. There is an inertial thrust direction, which is computed for us by Orbit's people, that tells us in which direction do we want the thruster to fire at each given time. And then we have sun direction, which we need to know at all times. In practice, during a real mission, this information would come from our sun sensors. Here, obviously, we're using synthetic data. That is kind of a lot to unpack. And so yeah, there's a lot of modules, and you can see all the connections between these modules highlighted by the arrows that connect each of those boxes. To try and break it down for you in a way that is a little easier to digest, I have broken it down into 3 parts. The first one of which is what concerns the platform actuation. The second part is the hub actuation. And the third part is the solar array actuation. And I'll start from the first one. So as I was saying, we are talking about a dual gimbaled platform connected to the hub. This gives us the direction of the thrust vector with respect to the hub. So the thrust direction and body frame components. It tells us where the thrust direction is with respect to our spacecraft. So the job that this part of software has is to maneuver the platform such that the thruster is doing exactly what we want it to do. In principle, we can align it with the system center of mass if we do not want the thrust to produce an external torque on the system. If we want to get a little fancier, we can articulate it such that the thruster is firing at an offset with respect to the center of mass, because that allows us to do momentum dumping. So if we have reaction wheels that are spinning at a very high rate and we ideally do not want that, we can try to make the thrust counteract that effect by dumping the momentum on the wheels. So the pieces of information that go into this module are a vehicle configuration message, which tells us where the center of mass of the system is. Currently, we are cheating on this because we are assuming exact knowledge of where the center of mass is. Future work will involve estimating the center of mass as it evolves throughout the mission. The second piece of information is the reaction wheel speeds, which are needed only when we want to perform momentum dumping. And as far as information going out, we have body frame heading, which tells us the orientation of the spacecraft with respect to the, the orientation of the thrust vector with respect to the spacecraft, and the torque that the thruster is producing on the whole body. So this is information in and information out. But what is happening within this block of code? The module that I call platform reference here is computing reference angles for the platform. So it's saying, in order to satisfy those requirements, you need to provide these two tip and tilt angles, tip and tilt, that are fed into these two PD controllers. Very simple. No need to describe a PD controller, I hope. And these PD controllers compute a torque that is then fed to our platform and thruster assembly, which are simulated components. Knowledge of what the platform is doing in real life is also fed back into the PD controller, because that's based on the difference between those reference angles and angle rates and the current angle and angle rates. That's how we compute the torque that actuates the platform. And also, because we are claiming to do high fidelity simulation, actuating the platform produces forces and torques that are fed back into the spacecraft, such that those forces are accounted for as we are maneuvering the whole system together. Very quickly, I don't want to get into the nitty-gritty details of how this software is structured and what the math looks like, but basically what it's trying to do is to take a thrust direction, which is that little blue vector over there, and compute angles that maneuver it such that it's fired exactly through the center of mass, or not, if we want to do momentum dumping. This is done through a proportional type of control law. And as far as testing goes, we only currently perform testing on the case where we do not want to perform momentum dumping. So the testing is carried out randomizing the location of the center of mass and computing the offset angle between the thrust direction and the location of the center of mass as it is given out by the platform reference generating module. Currently, this test allows us to reach a precision of 10 to the negative 8 radians. That's actually a lie, because I prepared these slides over a month ago. So in the meantime, we were able to push precision up to 10 to the negative 12 radians. This is to say, I forgot to say that every module that we have in Basilisk is unit tested. So we basically what we do is we run the code with a given set of input data, and we compare the output of the C or C++ module with some information that we believe to be true. So this is how we can ensure that everything is working according to plans. These are a few plots to show how all these things are combined together. In the top left plot, we can see the reference angles that are the output of the flight software module in dashed lines, whereas the solid lines are represent the response of the dynamic component as the torque is provided and this component is being actuated. The top right plot shows the torques fed to the dynamic component. We can obviously see that the torque is initially non-zero, and then it drops to 0 as we reach the target. More interestingly is the lower plot, which shows the offset between the thrust direction and the center of mass. So since we are trying to zero that offset, we can see that it's dropping to 0. So everything is working according to plans. The most interesting piece of code, in my opinion, is what relates to the hub actuation, because this is like the orchestra conductor of the whole spacecraft assembly, meaning that if this fails, we're not going to be able to achieve any of those pointing requirements. So what the attitude reference does is it receives an inertial heading that can be, for example, the direction that we want the thruster to fire along. So that's what comes from trajectory optimization. It also receives a body frame heading. In this sense, it would be the direction of the thrust with respect to the body. So what this piece of flight software code does is to make sure that those two overlap, such that the thruster is in fact aligned with the direction that we want. It also receives this celestial body message, which is nothing more than the location of the sun. Why does it need to know where the sun is? Because aligning the thrust direction with the inertial direction that we want locks 2 out of 3 degrees of freedom that are associated with an attitude problem. This means that once that direction is locked in place, we can still roll about that direction, and that gives us an extra degree of freedom to optimize something else. What that something else is the relative position of the solar arrays with respect to the sun, which is something that I'm going to talk about in the next few slides. So the attitude reference module receives all this information and it outputs an attitude reference message containing a reference attitude, a reference angular rate, and a reference angular acceleration. All this information, all this information goes to future modules, but it also goes into the attitude feedback module, which computes the torque that needs to be delivered to the hub in order to maneuver. This reaction wheel speed message, ideally I would have talked about it a little later, but it's a message containing measurements of what the reaction wheels are doing, and that is an output that feeds back into the previous set of code that I described, which is used to actuate the platform. Also, we receive measurements of the current spacecraft attitude and angular rates and accelerations, and those go into the attitude feedback module to compute a torque that needs to be delivered to the hub. Together with that, we also have the torque that the thruster produces on the system, and those two are combined and added together to compute the torques that go into the reaction wheels, which are this array motor torque message that goes into the wheels. Why do we have this other component of torque fed into this module? That is not strictly necessary. We could solve the problem without doing that, but the choice to do that is because if we did not provide this additional piece of information, the torque produced by the thruster on the system would effectively act as an unmodeled external torque, and it would have us rely more heavily on the integral term on the attitude feedback loop to achieve correct pointing. Whereas when this information is fed forward in this fashion, we do not need to rely as heavily on the integral feedback term. So whenever all our torques are mapped to the reaction wheels also exchange forces and torques with the spacecraft, and that allows us to actuate the spacecraft hub. I'm going to skim through this very quickly, but this is basically what I was just describing. So what this module does is to align a body frame direction with an inertial frame direction while also setting up a minimization problem that makes it such that the solar array rotation axis is as perpendicular as possible to the direction of the sun. The sun was supposed to show up in bright yellow, but I guess it's also, these lights are also feeling the weather conditions that we're having over this week. So that's what we're working with. These angles that I'm defining here, alpha is a mistake. That was supposed to be a beta actually, but these angles just depend on the geometry of our problem. And gamma is the incidence angle of the sun on the solar arrays. That's ideally 0. When that is 0, it means that the sunlight is directly perpendicular to the power generating surface of our solar array. So we are generating as much power as we possibly can. Why am I talking about this? Because gamma, as simulations showed, is a linear function of the angles beta and delta that are also functions of the geometry of the problem. This means that even though we obtained this nice plot on the right via numerical simulations, we can come up with an analytical formulation for the expected result of this module, which is simply the combination of 5 planes in 3D. This is very handy because it gives us the truth that I was talking about against which we can test the output of this module. So to unit test this module, we basically throw in a Cartesian product of however many choices of beta and delta and test the output of that with our truth model. And we are able to ensure a precision of 10 to the negative 10 radians. That's also a lie. We also pushed it to 10 to the negative 12. And these are a few cool plots to show that everything is working according to plans. On the left, we can see reference attitude at the top left, in the top left plot, and reference and actual angular rates at the left bottom left plot. And then top right plot, we have angular rates. The most important thing is the bottom right plot where we can see in solid blue, the angle between the commanded thrust, inertial thrust direction and what the thrust is actually doing. So we can see that it starts at an offset, but it drops to 0. So it means we have achieved the pointing requirement that we wanted. In orange dashed lines, it's the angle between the solar array axes, and the direction of the sun. So those are both going to 90 degrees, which means we are achieving the best pointing requirements possible, where we have both the thruster aligned with the direction that we want and maximum power generation. Last but not least, the solar array actuation. This is going to be very quick and easy. The information that goes in here is the reference attitude and the direction of the sun. This module receives this information and computes angle and angle rates. It also receives information of what angle and angle rates are, or what the solar arrays are currently doing as far as where they are and how fast they're moving. These two pieces of information go into a PD controller that outputs a torque, and the torque goes into actuates the solar arrays. And again, because this is a dynamic component, all these forces and torques are exchanged with the spacecraft hub. As far as the math behind this module, that's very easy. It's simply a linear algebra problem where knowing what the solar arrays are currently doing, where the sun is, we just compute an angle to rotate them by the desired amount. This is very simple math. So here we were able to achieve a pointing accuracy of 10 to the negative 12 right away. And here again, we can see reference angles for the two solar arrays that are being met. The torques drop to 0. And here we have, on the bottom plot, we have the angle between the sun direction and the power generating surface normal. So that drops to 0, which means, again, we are generating as much power as we possibly can. Because I've spoken enough, now it's time for cool simulations. So this is a simulation rendered through Wizard, so the cool visualization tool that I was talking about in the beginning. This is a simulation of what we call thruster point mode. So the driving requirement is what I was just discussing during this presentation. So we have a thruster that is firing, and we want it to be aligned with a certain inertial direction. Also, we want the solar arrays to point at the sun. It's moving. The platform is that little box at the bottom, so I think it's a little hard to see it move. But if you look at the solar arrays, you can see in yellow the direction of the sun, and in green the surface normal. So you can see that as the spacecraft rotates around, it drags the solar arrays with it. And as the solar arrays also rotate about their own axis, the angle between, or the offset angle between these two vectors goes to 0. So as we are maneuvering, we are achieving the pointing requirements that we want. This other simulation is what I called Earth point mode. Here we are not firing the thruster, so we don't really care about what the thruster does. So it's just not being actuated. That little box that represents the platform doesn't move. But in this case, the driving requirement is given by a body frame direction, specifically the direction of the high gain antenna, which needs to point at Earth. So the direction of the high gain antenna is here sticking out of the Basilisk logo right at the center of the spacecraft, whereas you can see that little light blue cyan line, which tells us where Earth is. So if we run this simulation, we can see that the solar arrays are apparently turning away from the sun. Now you're probably wondering what they're doing, but turns out they actually know what they're doing, because as the spacecraft rotates around to align the high gain antenna with Earth, the solar arrays are also informed of where they need to point at in order to achieve that pointing requirement. Let's give it a couple more seconds. Well, I'm already almost over time, so you're going to have to trust me on the fact that they do converge. So to conclude, Basilisk allows to simulate very complex spacecraft with articulating appendages. The modular structure keeps the code organized and compact, allowing for multiple instantiation of the same modules to simulate virtually identical components without code duplication. what does this mean? The solar arrays, we did not have to code them twice. We only coded them once and then created 2 instances of the solar array class and the PD controllers that actuate them and so on and so forth. All those PD controllers, we only coded them once and then we just made multiple instances of that. All cross couplings between moving components are accounted for in the dynamics. This is more relevant to a high fidelity simulation perspective, not so much as from a flight software perspective, but if the goal is to test our flight software in a realistic environment, we are pretty confident that what we have designed is very representative of a real spacecraft simulation. So yeah, the modular flight software allows to actuate each single component autonomously while preserving the flow of information between modules. Future work will investigate the use of different update frequency for different flight software modules. So here, every flight software module is called at the same frequency, but in the future, we want to experiment with that and see if there's any benefit in not doing that. So having components that are updated at a lower frequency versus components that need to be actuated at a higher frequency, depending on what the mission requirements are going to be. And with that, that's all. I will open it up for questions.